Hello, and welcome to your third lesson of Unit 5, where we're going to talk about titrations. We're going to talk about the basics of what a titration even is, and then we're going to start acid-base titrations by talking about strong acid and strong base titrations. So first of all, a titration uses a burette, which looks like this, very tall, okay? So, and it uses a burette because burettes allow you to add very small volumes. So, if you can see, this is closed. So if there were liquid in here, it would not. And then this is open, and so it would be flowing out. And then you can turn it to where it can even literally dispense drops at a time. And then, of course, it's marked, so then you can measure very specific volumes. Now, it is kind of backwards, so you do have to kind of practice reading a burette. So like if the level was here, we would read it, it's kind of hard to see. We would read it as like 40 point something instead of 41. We read from top down. Anyway, so that's a burette. You would sit it on a burette stand, and it would be above a flask like this. So it would be set up just like the picture shows, okay? So a titration uses a burette to add incremental amounts of a solution of known concentration, and so we call what's in the burette the titrant, to a solution of unknown concentration. We call that the analyte. So it's an analytical process that allows us to determine an unknown concentration. So we measure a certain property of the solution over time, and we keep adding the titrant until every bit of the titrant has reacted with every bit of the analyte, and we call that the equivalence point. And so at the equivalence point, then, we know that moles of titrant equal moles of analyte. So we know every bit of it is fully reacted. And since we know the volume and concentration of the titrant, and we know the volume of the analyte, I can then figure out the concentration, or the unknown. So we can use this equation, M1V1 equals M2V2, because, as I pointed out here, the moles are equal, and molarity times volume is moles. So this can be of my titrant, and this is my analyte. So this is my unknown, but I would know the volume, so I'd be able to plug this in. I know the concentration, and then once I dispense it and get to the equivalence point, I can then measure how much I added, so I'll know the volume. Then using this equation, I can calculate that unknown molarity, and we'll do an example of this. So titrations can be of anything that reacts, but we are going to focus on acid-base titrations. So that property that's measured over time is pH. And then we use an indicator to visibly be able to see when our solution flips from acidic to basic. Or in other words, when it neutralizes, it reaches the equivalence point, where all of one has reacted with all of the other one. So the point at which the indicator changes is called the end point. Now, if we use the correct indicator and proper technique, your end point and your equivalence point should be relatively the same. So you'll notice in these pictures, if we were starting, so you're almost always going to see this like pinkish purplish color, and that's because phenolphthalein is the most commonly used indicator for acid-base titrations. It's pinkish, like fuchsia, when it's basic, but it's clear when it's acidic. So you'll notice in this picture down here, we must be starting with an acid, and we're adding base. And right as it adds, we will see a little pink color. But as that pink color starts to persist, we know we need to slow down because we're getting very close to our end point. This beautiful, perfect little like pale pink, that's our exact endpoint. If we get to this darker fuchsia color, we've overshot our endpoint. We went past it. And so that's why you'll see in titrations, we always do a trial run so that we can get an idea of around what volume it takes to get to the endpoint, So then in our actual trials, we kind of can add it a little bit faster till we get close, and then we can start adding it dropwise so we don't overshoot that endpoint. So again, just taking a generalized titration and applying it specifically to an acid-base reaction, when we get to our equivalence point, then we know that our moles of acid have to equal our moles of base, because every bit of the acid has combined with every bit of the base to neutralize at our equivalence point. So we use this equation. It's the same as the one before, except instead of doing 1 and 2, I used A and B for acid and base. So we can either find an unknown concentration or the equivalence point volume if we don't know it. We always are going to know 3 of the 4 variables, and we can calculate the 4th. So I'm going to do an example of both. So in this first one, if I titrate 200 milliliters of HCl with 0.5 molar sodium hydroxide, and it requires 150 milliliters to reach the equivalence point, what's the concentration of HCl? So we have moles of acid, or excuse me, molarity of acid times volume of acid, molarity of base times volume of base. So I know my volume of acid, but I don't know the molarity. So that's my unknown. So I'm going to do, now, because you're going to be dividing these, you can convert these to liters or you can leave them as milliliters. It doesn't matter because you're going to divide the two together, so it really doesn't matter. So I'm just going to leave it in milliliters. Equals, and then we know my molarity of my base. And then after doing the titration, we knew it took 150 milliliters. So my molarity of my acid is equal to 0.5 times 50. 0.5 times 150 divided by 200. And so 0.375 is my unknown molarity of my acid. And I determined that by titrating it. Now, we might know our concentrations, and so then we need to know what volume it's going to take us to get to the equivalence point in order to work some calculations that you're going to see later. So this time, I know my volume and my molarity of my acid, and I know my molarity of my base. And this time, my question is asking me, how much base is it going to take to get to that equivalence point? So I'm going to plug in what I know, 0.2 molar times 100 milliliters equals 0.3 molar times my volume, and that's what I'm trying to figure out. So 0.2 times 100 divided by 0.3, it's going to take me 66.7 milliliters of base to get to that equivalence point. And it makes sense that it takes less base than acid because my concentration of my base is higher. So I mentioned that for acid-base titrations, pH is going to be the property that we're going to measure over time. And when we plot that on a graph, we call it a titration curve. So it is the pH versus volume of titrant added. So what we'll notice is we're going to have this huge jump in pH because that's going to be where we go from, in this case, acidic to basic. And right in the middle is going to be our equivalence point because that's going to be where we neutralize. That's where we flip from acidic to basic. So we can use this graph, whatever this volume is, that would be our volume of titrant needed, and we could use that to do our calculation. So on a titration curve, there's kind of 4 really important regions because they're regions where different things are happening, and it's going to be those regions where we're going to do different pH calculations. So the first region is just before any titration begins. So before the titration begins, all we have is whatever we're starting with in our flask. So if we're titrating an acid, then all we would have in here is the acid. If we're titrating a base, all we would have in there is the base. Then our next region is anywhere along this part. That's before my equivalence point. So at this point, I will have used up some of whatever I'm starting with, but I haven't used all of it yet. I haven't reached that equivalence point. So I'm going to have excess of my analyte. The next region is at my actual equivalence point. So that is where my analyte and my titrant are equal. So moles of acid equal moles of base, and I neutralize, or I flip to the other side. And then finally, anytime after that equivalence point, I have excess of my titrant. I've used here at this point is where I've used up all the analyte that I started with. So any point after that, I'm just having excess titrant. I'm just adding in extra. So something important to know about strong acid, strong base titrations. So we're starting with strong, both of them fully ionized. And so we're going to start with very low pH and we're going to end with a very high pH, or flip-flop. But either way, they're going to be pretty low and pretty high because we're dealing with strong acids and bases. Another key factor is that the equivalence point is 7. Because think back to salt hydrolysis. When a strong acid and a strong base combine, they create neutral salts. And so at that equivalence point, we are going to have a pH of exactly 7. And because they fully dissociate, there is going to be no equilibriums within a titration. Everything's going to fully react because everything fully ionizes. Okay, so what I did here is I kind of tried to write out the species that are present throughout this titration in the different regions. So region 1, as we mentioned before, is before titration has occurred. So in this example, we're doing a titration where HCl, hydrochloric acid, is our analyte, and we're titrating with sodium hydroxide. So the full reaction that's occurring is sodium hydroxide plus hydrochloric acid makes sodium chloride and water. But the net ionic equation is just hydroxide plus hydronium makes water, right? Sodiums and chlorines are spectators. But I have them listed out here so that you see kind of what's going on throughout the process of this titration. And what we're going to be doing with titration curves is we're going to be able to calculate the pH at different regions on the curve. So at region 1, we have not added any base yet. So all I have is strong acid, right? So if I were able to zoom into the molecules, I've left out water because obviously there's water throughout the whole process. But if I were to zoom in, all I would see was hydrogens and chlorine ions, totally separate, 100% ionized. So the only thing in the flask at this point contributing to the pH are these hydrogen ions. Okay, and so we'll see on the next slide to calculate pH there, we just do the negative log of the concentration of the hydrogen. Now, before I reach my equivalence point, I've added in some sodium hydroxide. And so you'll notice that I'm missing a hydrogen here. That's because the hydroxide reacted with the hydrogen to form water. But in adding sodium hydroxide, I also now have a spectator of sodium just chilling. But still, it's my excess hydrogens that are going to contribute to the pH. Now, when we get to the equivalence point, notice I don't have any hydrogens left. Because remember, at the equivalence point, moles of acid equal moles of base. It's totally neutralized. So the only thing I have left are these conjugates, the sodium and the chlorine. Well, like we said, strong acid, strong base makes a neutral salt. That's why this is a pH of 7. Because it's neutral, because sodium's neutral and chlorine's neutral and water's neutral. So we have pH of 7. Now, beyond the equivalence point, remember, I've already reacted all my hydrogen. So now I'm going to have an excess hydroxide. And so that is what is contributing to my pH, which is why now, past my equivalence point, I have a basic pH. So I'm hoping that kind of gives you a visual of what's going on. Like region 1, we have just hydroniums. Then we have less hydroniums than we started with, but still in excess of hydronium. Neutral at the equivalence point, and then past that, we've got excess hydroxide. So let's think about that. Now that we know what species are contributing to the pH, we can talk about, well, then how would we calculate it? So of course, when I have a strong acid and it 100% dissociates, then all of my hydrogens, whatever my concentration is, I'm just going to do pH equals the negative log. For region 2, I'm going to have used up some of my hydrogens. See how I have less? So I've got to do the stoichiometry or the molarity calculations to find how much is left and then take the negative log of that. For a strong acid, strong base titration, the pH at equivalence point, it's just 7 for the reasons I talked about before. We have a neutral salt and water, so it's just 7, no calculation required. And then at region 4, as we mentioned, we have excess hydroxide. So now I have to do the stoichiometry, I have to do the reaction to see how much excess hydroxide I have. Then, of course, take the negative log and subtract that from 14. Okay, so let's do some example calculations. So again, we have a strong acid with a strong base, and it tells us we're titrating 50 milliliters of 0.1 molar hydrochloric acid with 0.1 molar NaOH. Okay, so if I'm not given an actual graph or something to show me the equivalence point volume, I say always calculate your equivalence point volume so that when you're asked to find the pH when a certain amount of base has been added, you know which region you're in. It kind of helps organize your thoughts. So we're going to say 50 milliliters times 0.1 molar equals, I don't know the volume of base, but I know that it's 0.1 molar. So then, of course, 0.1 times 50 divided by 0.1, 50 milliliters is my equivalence point volume. So now, for example, number 2 says after I've added 30 milliliters, well, that, because I know the equivalence point volume is 50, I'm in region 2 at 30 milliliters. I haven't reached my equivalence point yet. Okay, so the first says, what's the pH before I've added any sodium hydroxide? So region 1, we only have strong acid. So pH is just equal to the concentration of the acid. So pH is 1. Right? So in region 1, we just do the negative log of the concentration. That's it. Now, I know I'm in region 2, like I said, at 30 milliliters because my equivalence point volume I determined earlier was 50 milliliters. So, at 30 milliliters, I'm at region 2. So what I have to do is I have to figure out how much unreacted H plus I have left over. So what I'm going to do is I'm going to determine my moles of each. So 0.1 times 0.05 is 0.005 moles of acid. And then my hydroxide, 0.1 times 30 milliliters is 0.03 moles. Now, as expected, my hydroxide is in the limiting amount because I am prior to my equivalence point. So I'm going to subtract 0.003. Now, I can put plus 0.003 over here, but water is not going to have anything to do with my calculation. So that leaves me with 0.002 moles and 0 hydroxide, which is what I expected because I'm in region 2. So now I'm going to convert this back to molarity. Now, my new volume, I already had 50 milliliters in my flask, and I've added 30 milliliters. So now I have 80 total milliliters. So I'm going to divide this by 0.08. And so my new concentration, or my concentration of excess hydrogen, is 0.025. So now I'm going to take the negative log of 0.025, and I get 1.6. So in region 2, we take the concentration of the excess hydrogen. So I always expect my pH in region 2 for this type of titration to increase because I've used up some of the hydrogen. Okay, so for strong acid, strong base, as we mentioned before, so 50 milliliters we determined was the equivalence point. So for strong acid, strong base, no calculations required. The pH is 7 because for strong acid, strong base, we're neutral at the equivalence point. Finally, for region 4, so we're past the equivalence point, we know that we're going to have excess hydroxide because at the equivalence point, every bit of my original acid has been used up. So now past that, I just have excess hydroxide. So I need to figure out how much excess hydroxide I have before I can figure out the pH. So I know I have 60 milliliters and it was 0.1 molar. So that gives me 0.006 moles. And then my acid, 0.1, and I had 50 milliliters of it to begin with. So as we expect, the acid is limiting this time. So that leaves me with 0.001 moles of hydroxide. Well, now I started with 50 milliliters and I've added 60 milliliters. So now my total volume is 110 milliliters. So I got to divide this by 0.11 liters. And that gives me 0.0091 molar hydroxide. So I take the negative log of that, is 2.04, which is my POH. So then 14 minus is my pH. So for region 4, we just have to do 14 minus the negative log of excess hydroxide. So nothing complicated, just taking care, turning it to moles, doing the reaction, turning it back to molarity. That's it. Okay, so all I have done here is I have just flipped it. Now we're starting with sodium hydroxide as our analyte and we're titrating with hydrochloric acid. So it's still strong acid, strong base, but now of course my region 1 is going to have a high pH because it's all strong base and we're going to end with a low pH. So all this is, y'all, is just flip everything. So now in the beginning, we only have strong base, so we only have sodiums and hydroxides, and so my pH is all going to be based on these hydroxides. So then at my, before my equivalence point, I have excess hydroxide, but less than I started with. Then I'm going to be neutral, again, pH of 7 at the equivalence point, and then after the equivalence point, I've used up all my base, and so now I'm going to have excess acid. So it's just like the last curve, just flipped. So in region 1, I have to just do the negative log of hydroxide and then 14 minus to get the pH. Region 2, I got to figure out how much excess hydroxide I have, negative log, and then 14 minus. And then again, at the equivalence point, no calculation necessary, pH is 7. And then after the equivalence point, got to calculate the excess hydrogen and then do the negative log. And I'm not going to do examples of those because we just did it. It's exactly the same. It's just this time you're going to be getting hydroxide in the beginning and have to do 14 minus, and then at your end, you're just going to have excess hydrogen and do the negative log.